Okay, today I thought we would work on another clearing an obstacle type problem. This time I want to clear a cylinder or a sphere or any object that has a circular cross section. Here's the idea. We have a smooth sphere that is fixed in place on a horizontal table or cylinder, and we want to project a projectile that just barely makes it over, clearing it on either side, perhaps at one point of tangency. Now, as indicated by the 1 here, we're going to do this actually two ways because there's two different interpretations to this problem. First, we'll assume that we really do just have one point of contact on either side, a bare grazing of tangency, and we want to work out what's going on here. We'll figure out what the minimum launch speed is. We'll figure out what the launch point is. In other words, how far away do you have to launch it at that speed, and also what angle is that. We could do this with calculus, but I think that some of these questions are better answered geometrically. So I'm going to use the AMGM inequality, that's the arithmetic mean geometric mean inequality that says the geometric mean of two numbers, positive numbers, which is their square root of their product, is less than or equal to their arithmetic average. So we'll try to use that at one point to save on some calculus work for minimizing. Okay, now the first thing we want to do is actually figure out what is this little angle, which I'm calling phi, where the projectile just barely makes a tangent contact with this sphere or this cylinder. Notice that this angle is between the horizontal and a radius of this circle drawn to the point of tangency. So hopefully we can try to figure out a relationship between phi and some of the geometric properties here. Okay, so the first thing we'll notice from the geometry is if I want to write down the height of the projectile at this point, meaning the height above the ground, I can just add the radius of the circle to this vertical component, which again, by right triangle trig, is just going to be r sine phi. So that's a nice geometric way of figuring out what the height of that point of contact is with the circle. Once I know the point of contact, or at least the relation here, let's actually use energy conservation. Or I guess more specifically, I want to use, let's use energy conservation to figure out the relationship between h and some of these speeds. In other words, I would love to know what the speed of the projectile is here. I'll call it v to distinguish it from v naught, the launch speed. So relating those two can come directly from energy conservation. We know that v squared will be v naught squared minus 2gh. This also comes from kinematics, so however you want to get to that is up to you. But now we have an expression for h. And this lets me write down v in terms of the initial launch speed and the height here. We also know that by symmetry, the other point of contact, the other tangent point, will be directly across the circle, and I can figure out what that distance is. Maybe I'll call that distance d or something. And notice that it's basically going to be twice r sine phi. So let's write that off to the side as well. Cosine of that angle phi. At this point, we can actually use some previously derived work because I know what the range, in other words, if this was my launch point and I'm coming back to another point at the same same vertical level, I can calculate what that range distance is in terms of this angle, which is not the same as theta. In fact, let me mark this. This angle here will be related to phi. In fact, it's 90 minus phi. We can see that because these two angles are congruent, and we know that this is a right angle because a tangent and a radius of a circle are perpendicular. So let's recall the range formula. D is our range in this case, and the range formula we derived previously says that that range for level ground is going to be the launch speed. Again, for us, the launch speed is the speed at that point, divided by g, and then sine of twice the launch angle. In our case, That's going to be 2 times this orange angle, which is 90 minus phi. Okay, so now we've got a few equations that we can start plugging into each other to see if we can find some constraints on that angle phi. So from our energy equation, the v squared is going to show up right here. Let's go ahead and simplify this. So on this side, we have 2r cosine phi, that's d from geometry. And then on the other side, we need to figure out how to handle this particular trigonometric identity. So notice there's a lot of ways of simplifying this identity. I think probably the easiest would be to expand it in terms of 2 sine of 90 minus this, cosine of 90 minus this. But you might recall that the cofunction identity says, and I'll write it over here off to the side, sine of 90 minus x is cosine, and cosine of 90 minus x is sine. So what happens is, if you do expand this out in terms of sines and cosines, each of the sines and cosines will just flip to the other one. You have one of each. And so you end up getting back just phi. So again, if you want to try that out or use an angle addition or subtraction formula, that's fine, but it's not so bad. We end up with just sine of 2 phi. You can also just remember that sine is symmetric about 90 degrees. Okay, let's solve this for v squared, so we can sub it in here. And I will actually go ahead and expand this out. So this will be v squared over g, 2 sine phi cosine phi. And the reason I'm doing that is because we can see that this cosine phi cancels on both sides. Okay, so the cosine phi's cancel, the 2's cancel, and now we can solve for v squared. Notice that when we divide by the sign, we're going to get a cosecant. So I'll have gr cosecant of phi. That's how we calculate the speed at this point of tangency. Now we can plug that in on the left-hand side, and we can plug in our h on the right-hand side to get an equation we can solve for v naught in terms of phi. Okay, so now we want to isolate v naught by moving some stuff around. Let's see. Moving this over, we'll have, let's see, gr. We'll have a 2 from the 2 times 1 here. We'll have a 2 sine phi from that. And then we'll also have a 1 cosecant phi. Now what I want to do is minimize. I want to find the minimum launch speed in terms of these angles phi. I could use calculus to do this, but I think it's nice to go pre-calculus and figure this out using our new tool, the AMGM inequality. Notice that 2 sine phi and cosecant phi is added here, which means the right-hand side of this inequality is kind of present in some way. The left-hand side, which involves the square root of their product, would have a square root of 2 sine cosecant, which is independent of phi. So this would be a nice way to find that minimum value. So I'm going to apply that inequality to these two terms. Let's see what happens. We get v naught squared is now greater than or equal to, because remember I'm replacing the sum with this product, gr times 2, the 2 out front doesn't change, and then plus, I have to move the 2 over, don't forget it's the mean, not just the sum, so twice the square root of 2 sine phi cosecant phi. But look, sine phi times cosecant phi is 1. I can pull out a 2. So v naught squared is greater than or equal to 2 gr 1 plus root 2. That means that the minimum speed must be the speed that saturates this inequality. So I'll take the square root, and I'll find that my minimum speed is root 2gr 1 plus root 2. How do you like that? No calculus involved. Okay, so we found our minimum launch speed. While we're at it, let me also mention that when we made this minimization, we might be interested in knowing when is this equal? What does it mean when they're equal? Well, the equality only actually comes up if A and B are equal to each other. So what that tells me is, at this minimum speed, I actually know what phi has to be, because at this speed, 2 sine phi has to equal cosecant phi. What does that mean? It means multiplying both sides by sine divided by the 2, that sine squared is a half. Or if you want, sine is 1 over root 2, which tells me immediately that this angle at which it's just barely tangent is actually 45 degrees exactly. So we get that as a kind of bonus as well. So now that we know this connecting angle where everything is tangent, and I know this minimum speed, we can figure out the rest of these fairly straightforwardly. Okay, so we found our minimum launch speed, and we also found that at this point of tangency in this problem, that phi is 45 degrees. Now I want to figure out where is the launch point. And let's note that this distance from here to here, which I probably would have called the range in a previous problem, I'll call it capital D in this case, can show up in the equation for our projectile pretty straightforwardly. I'm going to choose a coordinate system that's centered at this point of contact with the table, and in that case, the projectile trajectory has this form. I'm not going to derive that here because we've done that several times before, but notice that it has all the features we want. There's no linear term because of where I chose my origin. It's got to be symmetric around the y-axis. Sure enough, the maximum height, d over 4 tan theta, we did figure out at some previous point how the max height is related to the range, and indeed, the tangent of the launch point is like 4 times their ratio, so that's kind of nice. And then this bit out front was just rewritten in terms of tan theta and d. Usually we've been writing it as something like, what, g over 2 v naught squared cosine squared theta in the denominator. You can just wrap that all back up using our range formula d. And it's negative, of course, because it opens down. So this is the general expression for a projectile that's launched at angle theta with a range of d, symmetric about the y-axis. Doesn't have that linear term. And now I want to figure out where the launch point is. Now, I'm actually going to use a bit of calculus here, so we'll do a little calculus, I guess. And I need to know how this angle theta is related to this angle phi. And in fact, what I'll do is I'll just go to the other side over here. Doesn't really matter. And notice that at this point, or rather at either of these points, I do need the slope of my parabola to equal the slope of the circle. Okay, now for this circle, what I really want is to figure out where this point of contact is. And we do need to remember that the derivative of a circle at a given point, let's write it like this. If I use implicit differentiation to take the derivative of both sides, I can find that y prime is going to be negative, the 2's cancel out, x over y. Now here, since I've shifted the circle up by a distance r, it's y minus r. The important thing to recognize, though, is this x coordinate divided by this y coordinate is exactly cotangent of the angle phi. So if you don't believe me, try changing the polar coordinates here. X can be written as r cosine phi, y can be written as r plus r sine phi, and when you take cosine over sine, you get cotangent. So that's the derivative of the circle side. On the other side of things, we have the derivative of our parabola, and that'll just be minus 2 tan theta over dx plus 0. So these two have to be equal to each other at this point of tangency. Of course, not only do the slopes have to be equal, but the actual values have to be equal as well. So let's write that also. At these 2 points, I know that the y-coordinate of my projectile will just be what? R times, it's the h that we had earlier. So it's r times 1 plus sine phi. And of course, the y-coordinate over here will be negative tan theta over d. And let's go ahead and rewrite x as r cosine phi. And don't forget the constant term. So I need the slopes to be equal, and I need the two heights to be equal at this point. That'll give us a system of equations. And actually, while I'm at it, let's go ahead and replace this x also with r cosine phi for this point here where they are tangent to each other. Okay, let's go ahead, set these equal to each other, and get a system of equations on the board. Okay, so here are our two equations. Let's start by doing a little simplification on the top. Notice that both of these have a tan theta, so it'll be convenient to try to eliminate tan theta by dividing these two equations by each other. So I'm going to factor some stuff here and move it over. The thing I'll factor out will be a d over 4 minus an r squared cosine squared phi over d, and then have a tan theta. While we're at it down here, I'll go ahead and do a little simplification, noticing that if I divide out the cosine from both sides, I'll be left with a 1 over sine, which is cosecant of phi. Now I've got two equations with a tan theta on both sides. Let's divide these two equations by each other. And we end up with 1 over cosecant will become a sine. So that'll be the left-hand side. The right-hand side, the tan thetas will cancel. That was our whole goal. And we'll end up with something kind of complicated. Okay, not too bad, I suppose. Now what we want to do is we want to solve this for d. Okay, so let's go ahead and do a little cross multiplying. I'm going to bring this back up to the next board. I'll do a little bit of algebra in the meantime so we don't have to rewatch it and figure out how d is related to r and phi. Okay, when the dust all settles, it's actually pretty straightforward. The cosine squared on the previous board becomes a 1 minus sine squared. You can factor some things out. A lot of trig functions end up kind of canceling down, and we end up with actually a very straightforward final result for d, this range, in terms of r and this angle of contact. But we know the angle of contact. We did this generically without plugging in phi earlier because I'm going to do a second problem in a bit that changes this slightly, and I want to recall this result for that problem as well. But notice that in this problem we do know what phi is. It's 45 degrees, so I actually already know what this range is on the table. And if we just go ahead and rewrite this a little bit, we can distribute this 2 in and get that the range is just r times 2 plus root 2. That does mean that the launch point will be half of that away on either side by symmetry. So that's kind of interesting. It means, obviously, we do need to be launching it further than 1r. How much further? Well, 2 plus root 2 times further, which is about 3.5 times. So that gives us our launch point on the table. Now let's finish this off by finding the launch angle. Okay, so to finish things off, I'm going to actually go back to the equation for the derivative that I said equal to the circle's derivative and the parabola's derivative on either side. I've restored the original forms there. We now have this relationship for d, which is that it is 2r times 1 plus sine phi. Phi. And plugging that back in for d here lets us solve for tan theta. So let's do that. As before, the negative signs cancel. The cosine here becomes a cosecant on this side. And then we'll plug in our d here, although I'll multiply it back over. So we have cosecant phi times 2r 1 plus sine phi on the left. And then on the right, I'll have 2r over d well, sorry, I already multiplied the d over. We'll have 2r tan theta. Of course, the 2r's cancel on both sides, so we have that tan theta. Distributing this through will be cosecant plus 1. And plugging in the cosecant we had earlier, 45 degrees, and plugging in the 45 degrees into cosecant, which remember is 1 over sine, that'll give us tan theta is 1 plus root 2. Or if you want to have an approximate numerical value, I got about, I got exactly 3 pi over 8, or if you prefer, what is that in degrees? 67.5 degrees. Exact answer. It's kind of nice. So there is the launch angle. Notice it is, of course, larger than the 45 degrees by the time it kind of bends down when it touches the circle. And we have all three of the desired calculated quantities, QED.